Okay, let's go ahead and get started. Everyone can hear me okay? One person say yes.
Yes.
Yeah.
Okay, thank you. All right. Okay, so this is the week three. I just wanted to talk about chapter three and then a little bit of a chapter four. So we'll be doing chapter four um, uh, next week mostly, but this week you'll be finishing chapter three. There's a few things in it I want to talk about, but overall, if you've watched the lectures, it should be pretty straightforward. Now, from your end, what you're seeing PowerPoint, correct? Is that what you see as the big PowerPoint screen? And
Yes.
then, okay, because I've been trying to, for recording, I want to make sure that now when I stop, you see the big uh, dot cam. Is that correct? Okay. I think that should be the case. Just for if people watch this later and the dot cam's too small, it doesn't look very good. So, okay, so let's get back to it. So, I did want to briefly mention the quiz. And so, the quiz, about half of you got it all correct, which was good. Um, and then the rest of you got it in varying states um, of correctness, I should guess is another way to say it. So I put the solution up here. The solution's also posted online. If you want to look at it, I post all the quiz solutions and homework solutions so you can take a look at them. And I think the thing with this one on the those of you that didn't get 100% correct was I wanted to emphasize a couple of things. One was that the I gave you the unit vectors, and I saw that some of you went ahead and divided the unit vectors by their magnitude, which you found is if you square and square root them, it's one, which is by definition what a unit vector is. So that really didn't affect the problem because you pretty much got the same thing, except it ate up some time in the quiz. The other thing I noticed was some of you didn't have the weight of the actual tank in the z direction, and so when you did your IJK equations, you forgot to put W in there, and so I I I chose this problem in particular because I didn't want you to have to do three equations, three unknowns. So if you look at the way I've set it up, you have the tensions, and when you break them out into their IJK components down here, you can see that if you look at the Y components, they're the same. Or I'm meaning that TAB and TAC are equal. And so knowing that, if you can go back into the equation for the X, and since you know TAD, you can just basically say TAB and substitute it very simply, and then you can solve for TAC, and then you have TAC, TAB, TAD. Then you just come down here to the Z equation and plug that in. And a few of you had math errors, so but overall it looked good. So point is that I would just go back if you didn't, if you had a few questions on this problem. I would go back and look at the solution. Make sure you understand it. Again, the quizzes are more of an assessment tool for me to make sure that you guys are understanding the material, as opposed to something just meant to hurt your grade. So I encourage you to look at it if you don't understand it. And if you have questions, see me in office hours. Okay, so let's move ahead. Um, let's go ahead and quickly review week two stuff. So we talked about moment of force about the PowerPoint. And so we know that you always go, and this is something I know it seems like it's a obvious thing, but it's something that I've noticed over the years that people miss is that you always want to go to the force. So wherever your moment is, the point you're taking it about, you draw your R vector to the force. The other thing is your R vector is never a unit vector, because if you think about it, the R vector has a strong influence in the magnitude of the moment. The longer the moment arm, the bigger the moment. And if you make it a unit vector, then that would say everything in that direction would be the same moment, which doesn't really make sense. So never make the R vector a unit vector. And then once you have it, you have MO equals R cross F, and you're done. So it's I think it's something that most of you, after you do a few times, should understand. But again, if you have questions about it, um, either now or in office hours, please see me. Do we understand moment about a point? Any questions on that? All right.
I had a quick question.
Sure.
When you ask us for a moment at a point, are you looking for the vector or the magnitude, or do you want both?
So typically you would give me just the vector, and then the magnitude would just be if you were to square root them. And I generally don't ask you for that because I figure you can do it.
Oh, okay. But okay, I just put both on.
Oh, okay. Well, you'll get an extra happy face then on your
Okay.
All right. Thanks. Anything else on this? Okay, good. So another thing about when you're doing moments is if you have more than one force, then you can combine them all. So this example is out of the text, but it shows if you had, say, 4 forces and they're all at the same point, then you could either do R cross F and add them, or you could just add all the forces together, which I think is easier, and then do 1 R cross F. Now, of course, that assumes that they're emanating from the same location. And so if they're not, then you're going to have to just do as many R cross Fs as necessary. So you may have a body that has, 3 forces acting in 3 different locations. And in order to solve for that moment about a point, you would just add all those R cross Fs. So really it doesn't get much more complicated. You just have to keep track of each R vector and each force vector for your perspective distances. All right. Okay. So let's look at, this is an example. This is a projected force combined with a moment. And so here we have the megalodon, and so you have a 6-foot fishing pole, and you have you're assuming this tension on the line BC is 6,000 pounds. And so then you want to determine the moment about A. So this is a moment about a point, not about a line. And this one has a projected force. So this one's actually not, I'm going to go through it real quick, show you how it would be done. And I think most of you could probably surmise what would be entailed to do it. So here we have our drawing. So we know that this tension here equals 6,000 pounds. All right. And so what we want to do is we want to find our IJK components. And so we can see from here that this is going to be our Y component of the triangle. This will be our horizontal TH component. So what we can do is we can find, remember, our TH, which is our horizontal projection. That's just going to be equal to 6,000 times cosine 8 degrees. And so that gives us 5,942 pounds. And then we can do the same thing, since it's going down in the Y direction, then we can solve directly for the Y value. T in the Y direction is just going to be 6,000. It's going to be negative because it's going in negative Y direction. And that's going to be sine of 8 degrees. That's going to give us a value of negative 835 pounds. All right. And then lastly, we know that TX and TZ, they're going to be based on this triangle here. So we have, you see there's TH, so we know our TZ is going to be cosine 30, and the cross here is going to be our sine 30 with TH. So just like we've done before. So we have TX equals TH, and that's going to be times sine of 30, which gives me 5942 times basically 0.5, half, and that gives me 2971 pounds after rounding. And my TZ is just going to be, excuse me, TH cosine 30. That's going to be negative because it's going the negative Z direction. And so that's just going to be, again, 5942 times cosine 30. And that's going to give me a value of negative 5146. So now we have our three components of our vector. And so we want to know, we're looking for A, that's the moment, and B is on the point of the tension. So again, you can go from A out to C or anywhere on this line, except C is not really well defined, so B is. So we'll go from A to B. So we know that our B relative to A, so A to B to the force, and that's going to give us A basically 0, and then it's going to be 0I, and then it's going to be plus 6, and that's going to be for the Y, I'm sorry, that's going to be sine 45, and then minus 6 cosine 45. All right, so now we have everything we need, so we can go ahead and set it up. We know that, and again, I'm sorry, I should have drawn this first. This is our governing equation. Moment about A, got ahead of myself, equals R B relative to A crossed with that tension. So you always want to have that in there because that tells you that that's what you're doing. And that way I know exactly what the objective is and how you're thinking. So we set this up, and what do we have? We have R B relative to A, 0, 3 root 2, negative 3 root 2, and then 2971, negative 835, and negative 5146. And that's our tension. And so I didn't do the actual cross products. I know you guys can do it, but remember that your answer then will be a moment about A, and it'll be in IJK components. All right, and that's that. So this one was pretty easy. It just, the only thing is you had to combine this projected angle with the standard R cross F. Any questions? Good.
I have a quick question.
Sure.
About, what if instead it was like find the moment around like the axis A to B, where I think part of that equation is, you know, the distance from the moment arm to the force, but the force is directly on the moment arm. So would that just be 0?
If you're, wait, I'm not sure I understand. So you're saying if you're trying to find about a particular axis?
Oh yeah, sorry. I guess so like the moment about an axis, instead of a point.
Oh, I see what you're saying. If it was about an axis, so you're saying, well, if you picked, you'd have to pick a particular axis to define. So you could do the same problem, and if you wanted to have it about, you know, whatever axis there is in space, the difference with this problem is that you would add your lambda vector, right? So remember that. So let's say, for example, this part would all be the same. You would still go from, the only difference is the R vector when you're doing moment about a line is it's any point on the line to any point on the force. So for example, if I had, let's say I had a line that went like that, and we'll call it AD. So there's a line AD. And instead of finding the moment about A, I want to know the moment about line AD. So what I would do then is I would have to know, you know, what these coordinates are, and I would find the unit vector for AD. And then what I would do is I would come down here and I would just, whatever this result was, I'd have lambda AD dot product with this moment about A. And that would give me a scalar moment AD. Does that make sense?
Yes, yeah. It does.
And then would you then do the dot product with the scalar with the unit vector to get the components? Or yeah, or just multiply them?
Oh yeah, that's a good question. Yeah, if you wanted the individual components, that's true, you would. Because then you could break it down into its IJK components. Because right now this is in a magnitude. But you're right, you could break it into. But generally when you think of a line, the reason, I mean, part of it is the math, but when you think of a line, in a moment about a line is fixed in space. So it's either going to rotate clockwise or it's going to rotate counterclockwise. I mean, you can still have the direction of the moment, but it's basically going to be the same as the direction of the line. So all you're doing is you're breaking down the individual components that go in the individual directions in space. All right.
Okay, quick question.
Sure.
So I know like we can like in all your lectures you wrote all the things in IJK. Is it okay if we also write it in like instead in like the vector format, which is like the angled bracket?
Oh, you mean like this? Like where you're like 6, -4,
Yeah.
3? Yeah, that's fine. It's the same thing. Yeah, I don't care. It's the same thing. Okay, anything else on this one? Okay, so I just want to show one more line. This is this is kind of a summary of finding moments about a line, but here you have line OL is your, and I like this, wait, I haven't changed it. Sorry about that. Help if I go back to my slide. There we go. I like this picture because it really encapsulates what a moment about a line is, because I know sometimes it's hard to see, but if you have your force emanating from A out here in space, and then here's your point O. So if you just did R cross F, so the blue line crossed F, you would get this moment about O. And now you just take an arbitrary line in space, and all the line has to do is it has to pass through this point O. And so what we're doing effectively is anywhere in space this line is, you can draw a projection of the moment onto the line. And that's really what you're doing, is you're projecting this moment force onto the line. That's why you have this perpendicular symbol there. And sometimes it's hard to visualize in 3D. Some of you may be better at it than others. I know it's hard for me to visualize 3D. So I just trust the math on this, because what you're doing then once you have this moment, this IJK moment, is and that's why I had a couple of homework problems it's something they don't talk about in your text, but I put in a couple of homework problems talking about projecting forces onto lines. And I did that because that's exactly what you're doing here at the moment. You're projecting a moment onto a line. But I thought if you saw a force projected on a line, it might make a little more sense before you did a moment, because moments are a little abstract. Anyway, so this kind of describes everything that you have to go through. And it's almost like a recipe. And I'm not saying, don't understand the math, because of course you want to do that. But, in a pinch, when you're doing this, you really just have to follow the steps. You find your F vector, right? Whatever it is, in IJK components or brackets, whatever you want to do. You find your R vector, which is any point on the line to any point on the force, whatever's convenient. And then you find the unit vector for the line. And then you just do lambda dot R cross F, and your result is a scalar. And that's it. Anytime. And we don't really, and I know there's more advanced things you can do with it, but that's the limit which we do in this class. When you guys, for some of you fortunate enough to take intermediate dynamics as MEs, you'll get into all kinds of 3D vector math with moments. So, but for now, that's not something we need to deal with. All right. Any questions on moments about a line? Okay. So this week you'll be looking at, actually here's an example of one moment about a line. But I think given time, it's already 8:30. I think we have time for it. Let's go through it real quick. It's not a real difficult problem. In this case, this will just kind of sum it up. So in this case, you have this box, and I've drawn a line in OD going from the origin to the point D in the corner. And I've asked you to find the moment about OD by this force up here, this -6, 3, 10 up here. And so if you look at the drawing, so here's my drawing here, and I have my force, -6, 3, 10, and then I'm given OD and my force. All right. So, and then so I want to find moment about OD, and I want to find the vector OD. So this kind of goes back to the question asked earlier about finding this in vectors. I think that was Liam who asked that question. So, so we have moment OD equals lambda OD dot, and in this case, I'm going to say R, and I'm going to say B relative to D. So here's point B, sorry. And I can say B relative to D. So I'm going from D to B, and then I'm going to cross that, of course, with my force. So there's my governing equation, the whole thing right here. So, and I know that once I get the moment OD, that's going to be equal to the vector OD is just going to be equal to scalar OD dotted with lambda OD. And so this is kind of equivalent to what we were doing with the projected forces. So this second part here, I don't ask very often, but I wanted to show you just in case it does come up. So first off, we want to get lambda OD because we want to know what that is. Right. And so lambda OD, we can see we have our coordinates. So it's going to be 3 in the I, right? So we're going just from O to D. So 3 in the I plus 3 in the J plus 1.5 in the K. And if we square root that, we get 4.5. So this really gives us, to simplify it, 2/3 I plus 2/3 J plus 1/3 K. So I'm just going to leave it in that form. And then I need my R, B relative to D. Sorry. And that's just going to be equal to -3I. So I'm just going to go from D to B and just go -3. So you can go from O to B. That would work. You could pick a point in the middle there and go, but why make it hard? Just pick the easiest point to go to. And then lastly, we have our force, which we're given as -6, 3, 10 in brackets. All right. So we go ahead and set it up. Moment OD, and that equals lambda OD, R, B relative to D, and our force. And we go ahead. 2/3, 2/3, 1/3, -3, 0, 0, -6, 3, and 10. Okay. So this one, there's not, because there's so many zeros in there, we get essentially 2/3 times 0. And so there's no IJKs because we're basically saying I dot that cross that. So they cancel out. So we're just adding these scalar components with us. So now we have 2/3, and then that's 0 minus -30, and then plus 1/3 -9. So if we add up everything I get 17. Okay, after I do that. So my answer technically is 17 Newton meters, or proper sig fig, 17.00 Newton meters. So most of you are following the sig fig convention, but just remember that if you have a number that leads with a 1, then you should have 4 sig figs. Any number that leads with a 2 through 9, then you only have 3 sig figs. And just try to remember to do that on your homework. So on the last homework, if you saw I wrote watch sig figs, that's what I was referring to. All right. And then, so now if we want to convert that to a vector, then we just have MOD, and that just equals 17 dotted with the unit vector, right? So the unit vector is up here. So, so dotted with lambda OD. And so if we do that, I know you guys can do that. I'm just going to write it real quick. You end up with 11.33 I plus 11.33 J plus 5.67 K Newton meters. Always important to have units. So that and that. All right. All right, good. Okay, so moving on, since I want to be sure to get to the new stuff.
Professor.
Yeah.
So this week 3's material finishes chapter 3, correct?
Yes, it does.
Will the quiz be entirely though on the chapter 3 content from week 2, or some of the next week's lectures as well, or I guess this week's lecture?
So the quiz at most would have what's on today's lecture, but I can tell you, so what you're covering in today, I believe is, let's see, what is today? So today we're the 12th, so couples and forced couple systems. So I'm going to show you that. I would say that the quiz would cover moments about a point, moments about a line, and possibly couples and forced couple systems, which is today. So those 3 topics, that's it. Nothing beyond that. Nothing from chapter 2 either. It would just be that. Okay.
Okay, thank you.
Yeah, no, I was going to say that, but thanks for getting to it. And so here we go. Let's talk about week 3. So the rest of week 3 is really talking about equivalent couples, equivalent force couple systems, and equivalent systems. And then you'll start chapter 4. So that's chapter 4 is fairly easy. So if we don't get to it today, the very beginning of chapter 4 is pretty straightforward. And so we're about 20 minutes. So I'm going to go a little faster now. But I want to make sure we get as much as we can. So this is the idea of the force couple system. And I want to explain this. I think if I explain it on paper, it might be a little easier to understand. But let's start with what we have. So if we look at these 3 diagrams that I have down here, imagine that you have a force acting on a rigid body, and you have this point O and you have this point A. So we know that we can create a moment about O if we wanted to. But let's say for whatever reason, if we have this force in this certain part of the body that maybe the material isn't strong enough, it's a system, and we want to move the force somewhere else, but we don't want to disrupt the overall equilibrium. So if we were to just take that force F and move it to O, well, if we do that, obviously that's going to change something. But what we can do is if we do that, we can add a moment, which will make it equal. Now, what does that mean? So let's look at the next picture. In the next picture, what we're doing is we're adding an equal and opposite force to it. And then in the last picture, we're taking that equal and opposite force, and that forms a moment. And then we've now moved our force and we now have a moment. So now I've said that, but I want to make a few drawings because I think it's It'll be easier if I just walk you through it. So for one is this, when we talk about couples, the first thing in the chapter, all a couple is it's two forces that are equal and opposite. So if I have a couple like that, let's say I have 10 newtons, and that's 10 newtons, and the distance between it, let's say, is 5 meters. Now, what's the magnitude of that couple? What do you think?
10 newtons.
Well, it's a couple, so a couple is a moment. So couple equals a moment, synonymous. So a moment is in Newton meters. So what is the magnitude of that? What do you think? Is it 50 or is it 100? What do we think?
50.
It's 50. That's right. And why is it 50? Because some people say, well, you have two of them. But if you think about it, if I take this point here as my origin, then I say, how far away is that? That's 5. And how far is that? That's 10. So that makes 50. If I went from the middle, I'd have basically 2.5 times 10 plus 2.5 times 10. So it'd always be 50. And that gives me 50 Newton meter couple. That's all that is. And so couples are just equal and opposite. And they're just they're a moment, but they're just a special case where you have this equal and opposite forces. Now, we use this concept when we were trying to figure out a equivalent force couple system. So oftentimes the wording of these problems will say replace force at, and it'll be a letter, usually A, with an equivalent force couple system at O. And that's how it'll be worded generally. So again, if we get back to and I want to walk through that drawing. So you have your blob, and let's say you have your force. Okay, so here's your force, and here's your point here. So that's O and that's A. Okay, so I don't want that force there. I want to move it here. So if I draw an equal and opposite force, right? So this would be F minus F, and I still have this F here, right? So I haven't done anything because these cancel each other out. So this and this are equal. So this again is still point A. This is point O. This is equal. So you don't have to worry about anything changing. But you notice that if I combine this and this, that is a couple. It's two forces equal and opposite of equal magnitude. And so what's the distance between them? That line there. Now, when I've drawn this up here, that's a 2D couple. So that assumes that this is perpendicular. But that doesn't have to be the case. Because remember, we can do R cross F, and that accounts for any vectors that are in more than 2 dimensions. So what we end up with then is, in order to figure this out, our answer then is, when you say replace force at A with an equivalent force couple system at O, first off, your answer is, what is F? So that's part of your answer. F equals whatever the original F was. So if you do nothing else but write the force I give you, you've gotten part of the problem correct, right? So you just write it out in its IJK components, because that's part of it. And then the next part is the moment. And then the moment, of course, is just going to be R, A relative to O. So and that's the thing sometimes it's hard to remember, is that you always go from the new point to the old point. So I'd make a note of that in your notes to say, and I do go over this in the pre-recorded lectures that you'll watch, but you always want to go from this point to that point. So R, A relative to O crossed with F. And then of course that's going to give you some moment. So that's why in the final drawing, you have something like this, where you have a moment going off like that, and then you have, your force like that, and everything's peachy. Okay, does that make sense to everybody?
What was the force representing Oh, so can you explain the last drawing with the M and the F?
Oh yeah, so here's point A. Is remember I moved the force to O, so that's what this is. I guess I should have drawn it in that. I should have drawn moment going like that. That would have been, and then the force like that. Sorry, it's getting really messy, but and then forget about that. So all this was this force here is this force here, right? Because I've moved the force physically to O. So when it went from here to here, this went from here to here because I had an equal and opposite. So this and this became a moment, and that became the force. That's why you end up with just, let me redraw it. You end up with just something that looks like this. Here's your 2 points. There's A, there's O, and a smiley face. And then there's your force, and there's your moment. All right. Does that make sense, everybody? So let's do a quick example with actual numbers, and I think maybe that'll help a little bit. And where'd that example go? Oh, here you are. So let me go back. Let me show you the drawing. So here we have, there we go. Replace the force F2. So there's F2 with an equivalent force couple system at O. So O is over here. So take a second to draw this, and I'll have it on my drawing too, but so you have O coming out, then you have the pipe straightened out, and then it comes up, and then you have your force coming off. So the important part of this is to figure out what is the R vector going from O to A, right? Because you always want to go from the point that you're moving to A. So if we do that,
I think we still see the PowerPoint.
yeah, no, I'm going to switch it back.
Oh,
Thank
okay,
you.
sorry.
No, thank you for pointing that out. So here we go. So here's my drawing, and then so we'll just walk you through the problem. So you have O relative to A. So here's our force, -10, 25, 20, and that's at A. And then we want to find the equivalent force couple system at O. So first off, we figure out what is this vector going from O to A. And so if we do that, if we know that it goes based on the drawing, we know it's 1.5 because O is at the origin. So we know it's 1.5 in the X. We know that it's out to 4 in the J and in the Y direction. And we know it goes up 2 in the K. So that's pretty easy to find that. And then we just cross product it with that. So if we do that, we end up with -20, -50 plus 77.5. So our final answer then, once we've done this, is just what you would write is you would write the force as, and you could do it in brackets or out, but -10, 25, 20 in pounds, and then the moment about O, and that would just be -20.0, -50.0, and 77.5, and that'd be in foot pounds. Just make sure you have your units. And so there's your answer. So I think the math on this, again, you see is fairly easy. It's just the important thing is understanding, what is actually going on. What are you doing? And all you're doing is you're moving this force to O, and then you're compensating it with a moment so that the system remains the same. Okay.
Professor?
Now, yeah.
What changes mathematically? Because I understand how we're like moving the force to a different point, but it seems kind of just like similar to what we have been doing.
Right. So, well, what changes is what you're doing effectively is you're moving this force to here. So this force is coming, is becoming there, right? And now when you move that there, you have to account for the effect that, because remember that we're assuming, these things are in equilibrium, but we're not setting things equal to zero. So what we're saying is that there's some force somewhere that's holding this in place. So that's why we say we're saying, what is the resultant moment? We're assuming that something is countermanding that to hold this system in equilibrium. So when we move this force here and there, then we're essentially saying that a moment, by moving it from here to here, that system is going to experience both this force and this moment. And that's good. And that's what is required to move this force from here to there. So mathematically, nothing's really changing. I know it does seem like the same, but again, all you're doing is you're just adding this moment to compensate for the force change. Now, in some cases, you may want to have multiple forces where you want to have something equivalent. So, for example, and this idea we use in chapter 5 when we talk about centroids, and because I know you guys have already talked about centroids in your calculus class. So if you think about it, if you have a bunch of forces acting on a plane, it's possible to write one equivalent force for all of those forces at a given location. And so and we'll focus just on in one dimension here, but if you think about it, like say your xz plane has these three forces acting on it, you can then add those up and you can calculate where you could put one equivalent force, which is over here, that would be the same as that. So think of it another way, like there's an example problem in the book. It says where you have three children standing on a raft. So the raft's floating, and so they're standing in different parts of the raft. The raft is like 5 by 5 meters. So you could take the three off and you could replace them with one equivalent force at a similar location that would be the same as the three people in the different locations. So, and it's not really a difficult process, but let me show you an example. So here we have, this is just 2 dimensions. And again, remember, this is just what I'm going over highlights. You'll go over more examples in my lectures. So this isn't meant to be a substitute for the lectures I have. So here we have these 3 forces acting on this plate. So what we want to know is we want to replace these parallel forces with a single force, and we want to know where it would act. So we know 2's up here, 5's there, 3's there, but where would we put that resultant force so that it had the same thing? Now, one thing you can see right away is that these forces are going to cause a moment around the x-axis and around the z-axis. So we're going to need to find a z location and an x location. All right, so let's look at that. So here what I've done is there's our drawing, okay? And I'll give you the location. So we know that the 2 kilonewtons, that's at 1.5, 0, 2.5. That's its location. 3 kilonewtons is at 1.5, 0, 0.5. And then the 5 kilonewtons, that's the x-axis, is at 0.5, 0, and 1.5. So those are just their respective locations in space. So for example, the 3, this would be 1.5, and this would be 0.5. So we want to replace, we want to find equivalent R and its location. Okay. So what do we do? Well, as I said, you can see that these forces here are going to cause a rotation about the x-axis, right? They want to make it go like that. So we can do that by summing the moments about the x-axis. And so if we do that, we know that force 1 times its z location 1 plus force 2 times its z location 2 plus force 3 times its z location 3 equals the total resultant times z resultant. Okay. And this is what we want to solve for, right? We want to know where it's at. Now, R is easy. R is just just the sum of these forces, right? We know that we do the math and we know that R is 10 kilonewtons, right? So we want to take this 10 kilonewtons, the sum of these three, and find its specific location it's at. So if we do that, we can say 2 kilonewtons and its z location is 2.5, and then plus 3 kilonewtons and its z location is 0.5, plus 5 kilonewtons and its location is 1.5, and that equals that equals 10 kilonewtons times ZR. So this one's actually not so hard because this is 5. You can do this in your head. This is 1.5. That's 7.5. So, and this is 10. So you end up with 14 divided by 10 equals ZR. So my ZR location is 1.400 meters. All right. And then you just do the same thing with the other one, summing the moments about the Z. And if you do that, just set it up the same way. In that case, it would just be 2 times 1.5, and we're out of time, so that's why I'm going quick, plus 3 times 1.5, plus 5 times 1.5, and that would be equal to 10 times XR, because you want that. And it turns out that XR, if you check it, is 1.00. So what you find then is that here's your XR and there's your ZR. So you find these two new locations, 1.4 and 1.0. And this is really the same concept as the center of gravity, isn't it? You add up all the individual forces and you find the average center. This is just the difference, only using 3 finite forces. Does that make sense? So that's pretty much everything in chapter 3. They're equivalent couples, equivalent force couple systems, and resultants. So I pretty much covered everything in chapter 3. We didn't get to chapter 4, but we can cover that. So any final questions on this? So I will be in my office between 10 and 12 if you guys have any other questions. So please feel free to stop by and ask anything. But otherwise, I will see you guys next week. Thank you.